Hello mathematicians, we're now going to have a look at recurring decimals and geometric series, and we're going to make the discovery, if you like, that recurring decimals are essentially infinite geometric progressions. And because of the nature of recurring decimals, we're going to show that their value is the limiting sum of a GP. So if we had this particular recurring decimal, now it would be really good if you could go back before you get too tangled up in this option, go back and have a think about how you would have done it in the prelim year. So in terms of saying something like let x equal this number, then taking a look at what a certain multiple of x is to get the decimal point to here, and then another multiple to get the decimal point to the end of the recurring bit, and just revise that little section. But for the moment we're going to concentrate on just this recurring decimal pattern and using what we now know about GPs. So if we recognise that 2.645 repeater is this, then we need to break it up into decimals of our repeating section. So that's 2.6 plus 0.045 and then 0.00045 and so on. And you can already see the pattern, I'm sure, that what we have is 2.6 plus an infinite GP, so that's this part here, with A equals 0.45 and the common ratio being that we're multiplying or dividing effectively by 100. So R is 0.01. If there were three figures between the two dots, R would be dividing by 1000, so it would be 0.001 and so on. So once we realise that fact, then we simply use the limiting sum formula just there to work out what our sum to infinity is for the recurring part. Now when we do that, you can do it on the calculator, so I'm just going to bring the calculator up here in a moment and look at how we can do this in terms of using the fraction key on the calculator. So if I just concentrate on the limiting sum part for a moment, it's 0.045 over, and I can do the 1 minus 0.01 if I'm not comfortable doing that in my head, and I get this. But we don't want this because this is not an exact value, it's the calculator approximation. But if we just simply use the switch between fractions and decimals, we get our 1 on 22, which is what 45 on 990 is. 45 goes into 990 22 times. And then our 1 on 22 plus, let's just say 2.6, and we get this thing. And again, we can go floating point to decimal and get our 291 on 110. So if we look at this working out here, that's going to give us 291 on 110. So the calculator can offset perhaps your lack of comfortableness, if that's the case, with fractions. So once again, this is the only question I'm going to get you to do on this, because it's not a big mark getter, but when it's there, it's marks to be grabbed, basically. But again, I want you to compare what we did when we worked it as sort of a fraction problem back in prelim, what we're doing with the GPs, and why the GP section works, and then have a go at that question. Make it not a reliance on memory, but a reliance on process.